Nope. Okay, great. Okay, so today we're going to be carrying on discussing adaptive dynamics, which we introduced on Monday. And we're going to be talking in particular about a concept of evolutionary stability. So we talked about evolutionary stability or evolutionarily stable strategies in evolutionary game theory. And this is very related to that, but ultimately it's slightly different to what we looked at previously. So there are definitely some similarities. There are also other types of stability, in particular convergence stability, that we'll talk about after the midterm when it comes to adaptive dynamics. And that's because this evolutionary stability doesn't tell you about the evolutionary process, it tells you something about the endpoint. In a similar way that evolutionary game theory with ESSs or Nash equilibria tell you about potential endpoints or steady states. Okay, so we're going to go through this today. Last time we went through replicated dynamics as a way of kind of bridging the gap a little bit between evolutionary game theory and adaptive dynamics. Remember, these are methods for modeling phenotypic evolution, so not things like allele frequencies or genotypes or haplotypes. That's all population genetics. Here, when we're doing phenotypic evolution, we're thinking about characteristics or traits. So we're going to be treating these as continuous traits as well. They don't have to be, but if we can at least approximate them by continuous traits, then that's fine. What we're really assuming is that rather in population genetics, where we focus on a few major allele effects at just a few loci, maybe one, two, a relatively small number, we care about those genetic interactions. Here, we're kind of like overlooking those genetic interactions, and we're thinking about, okay, all those genetic details, and we're assuming that there are lots and lots of loci that each have a relatively small effect. Okay, so at the end of the last lecture, we considered a simple example of how, if we looked at the per capita growth rate of, say, of an individual, but it should really be the phenotype, how the relationship between the per capita growth rate of those individuals with that phenotype depends on that phenotype. And remember, we had like a quadratic, and we said, okay, well, we should end up at this this maximum here. This is kind of what we want to do with adaptive dynamics. We want to work out what's going to happen in the long term. And we talked about this process of mutation followed by invasion and ultimately replacement. And we keep iterating this process, and that kind of gives us an evolutionary trajectory for our phenotype that we're interested in. So we're going to explore this in a bit more detail today, and we're going to look at a model of intraspecific competition. So intraspecific, the intra means within, so intra is within, species specific, so within a species competition, so not competition between species. So you can think of this as between different phenotypes. So maybe some individuals within a population or within a species have a larger body size, smaller body size. Maybe they have different preferences for where they eat, what kinds of foods they eat, where they get them from, where they nest, all of those kinds of things. Okay, so there's quite a few things to introduce today. Many of these things we'll be visiting again over the course of, I guess, over the second half of this course. So today we'll talk about intraspecific competition, which I've just talked about. Within that, there's ideas of intrinsic growth rates and carrying capacity. I'll explain these in a moment. And then when it comes to adaptive dynamics, we've already talked a little bit about invasion fitness, but we'll also talk about selection gradients, singular strategies, and then this concept of evolutionary stability. These four things here, they'll be appearing time and time again, so definitely pay extra attention to these. Okay. So let's think about a basic model of intraspecific competition. Okay, so this is actually known as the Lotka-Volterra model. Lotka-Volterra also did a model of predator-prey dynamics. Don't confuse this with the predator-prey model. That's a Lotka-Volterra model. And this is a very classic model of modeling competition. Okay, here I'm going to refer to it as an intraspecific. It can be competition between species as well, but we're just going to focus on an intraspecific one because we're interested in how the phenotypes within a particular population are changing over time. Okay, so the equation for this is dni dt, where ni is the number of individuals with a particular phenotype. The phenotype I'm just going to refer to as x sub I. Okay, so the rate of change of individuals with phenotype xi is dni dt. And this is going to be equal to Ri, which is the intrinsic growth rate of individuals with phenotype xi. This should really be intrinsic per capita growth rate. This Ri, this intrinsic per capita growth rate, is multiplied by the number of individuals of that phenotype. Now, if this was just a model like this, then this gives you a model of exponential growth, right? You can do separation of variables here, solve this, and you'll get an exponential. So we know in general that populations they might grow exponentially for a little while, but eventually they're going to deplete resources, and that's really where this idea of competition comes in. So this intrinsic growth rate is then modified by what we refer to as density dependence. Okay, so as the density of the population increases, as the population size increase, then resources are depleted, whatever those resources happen to be. And so we would expect there to be stronger competition when there are more individuals around, and therefore that lowers the growth rate of the population. Okay, so we therefore have this density-dependent competition term, which reduces this factor here. So we have 1 minus, so this 1 is just basically saying, what do we start with? What's our intrinsic growth rate for these phenotypes? And then we're going to sum over all possible phenotypes in the population, Nj. We're going to divide by the carrying capacity of the population. There's something else that goes in here as well, which I'll explain in just a second, but this carrying capacity, Ki, is basically saying how many individuals of phenotype Xi, if the population was entirely composed of just that phenotype, could this environment support? Okay. The other thing that we need to include here, because we're thinking about competition between phenotypes, is we need to think about the interactions between phenotypes. Even if these might be direct interactions, as in, they're actually physically competing with each other, they might be indirect because they're both exploiting the same resources, and therefore there's less resources around. Okay. So what we're going to do is we're going to sum over all possible phenotypes J. I haven't actually stated how many there are here. We can just, however many there happen to be in the population. And then within this sum here, we're going to multiply this Nj by a factor A sub ij. And this A sub ij is the competitive impact of an individual with phenotype Xj on an individual with phenotype Xi. Now, if there was just one phenotype in the population, and we would typically set this A II, so when I is equal to j, equal to 1, then in that case, you would end up with dn let's just call it dn dt in this case, Rn 1 minus n over k, which should hopefully look familiar to you if you've seen a logistic model. Okay, so when there's just one species here, this model collapses down to your classic logistic growth. When there are more species there, we end up with this Aij term potentially being, it could be greater than 1, depending on the scenario. It could be less than 1 as well. This tells us something about, we'll get more into this in future lectures, about the degree of overlap between the resources that individuals from phenotype I and J might use. Yes.
And IJ is obviously just for two organisms. Right?
Sorry, say again.
IJ is just for like two separate organisms.
So they're different phenotypes. So you could think about, and we're going to assume as well here that those phenotypes sort of are heritable. So individuals with phenotype Xi give birth to individuals that have phenotype Xi, and likewise those with phenotype Xj, free true, they reproduce offspring with phenotype Xj. What those phenotypes are, we haven't actually stated, but like I said, they could be things like body size. So this could be smaller versus larger individuals. In the context of like birds, I don't know if anyone's familiar with like Darwin's finches, but there are lots of different birds on the Galapagos Islands. They have different beak size, and they specialize on different seeds. So they might be birds that prefer small seeds versus large seeds. Maybe there's a bit of overlap between them, and therefore they compete a little bit. Maybe they compete a lot. Okay, so this is in its most general form. We haven't actually stated what these phenotypes are. There could be any number of phenotypes. So you said 2, there could be many, many different types. Okay. So this is the general model. And one thing we're actually going to assume here straight away, just to simplify it a little bit, we're going to assume that all of these phenotypes have the same growth rate. So we're going to assume that Ri is equal to R for all I. Okay. There's no variation in this intrinsic growth rate. In the most general model, yes, you can have this, but we're going to simplify it a little bit. Okay, any questions about the basic structure of this model? You're good? Okay. I just have a show of hands who's met this model before. Okay, one there. Mark, your hand should be going up because you've met it in Math 360. Okay. Right. So let's think about how we then model evolution in this model, in this sort of intraspecific competition framework. Okay, so we're saying here in this model, if we ignore the Ri because we're going to set them all to be the same, we're assuming there's variation in these two terms here. Okay, in this competition term, somehow depends on the phenotypes of xi and xj, and the carrying capacity could potentially depend on the phenotype of xi. So why might these happen? Well, like I said, these phenotypes could in principle be any sort of morphological, things like body size, physiological properties, traits, or it could be a behavioral trait, their preferences. That could include things like who they prefer to mate with, where they prefer to nest, all of those kinds of things. These are our phenotypes, and we're going to assume that xi is just some real number. If we're doing something like body size, obviously this needs to be a positive real number. And we're going to assume that this trait affects the carrying capacity of the population. So if the population was composed entirely of just xi individuals, then it would tend towards a carrying capacity of ki, which is just a function of its phenotype xi. I'm going to call this k hat, which is just some positive number, e to the minus xi squared. So this is just some k hat greater than 0. So we can sketch a graph of what that looks like. Pretty simple graph. We've got our phenotype xi varying. We've got our k of xi here, and looks like a Gaussian, basically. Something like this. Shouldn't go under the axis. And hard to draw on an iPad. There we go. And it peaks here, k hat, when xi is equal to 0. So I've assumed this function, but why would I assume that there might be a relationship between phenotypes, these kinds of characteristics, and a carrying capacity for individuals with those phenotypes? Any ideas? Yes, Mark?
Well, if we had like a bunch of smaller individuals, perhaps there could be more individuals there, just because there's less of them, so they're consuming less resources.
Yeah, so it might be something to do with like use of resources. I've arbitrarily set this to be 0. This phenotype here also could just be translated somehow. This could correspond to some environmental properties, basically, where an environment, when I say environmental properties here, it could be, let's think something. Maybe this is perhaps a spatial location along some kind of gradient. When you're below this level, it's too, if this is like translated from 0, this was some kind of reference height above sea level. Perhaps below that, it's too warm, and above that, it's too cold. And there's some kind of like Goldilocks zone here, where it's just the right temperature, which supports enough food for your population to grow. So it could be anything basically that from an environmental perspective maybe modulates that. It could be the degree of competition with other species. This could be something like even kind of abstract like coloration that individuals have. This is a measure of the like plumage that birds have, the types of colors that they have. And maybe if they overlap with other individuals, other species, then they're going to compete with those. It's going to cause confusion. Therefore, when they're different, that's the best thing. So there are lots of different traits in which this kind of thing could play into carrying capacity. So, for example, some morphological traits. e.g. body size, may be more efficient than others. Efficient in the sense of being able to exploit the resources in the environment. Okay, so we've got a function here for K, or Ki, and we're also going to assume that the strength of competition between individuals with two different phenotypes, well, they could be the same phenotypes, so phenotypes Xi and Xj is going to be Aij, and this Aij is just a function of Xi and Xj. And it's going to look fairly similar. I'll assume again a negative exponential, a Gaussian here, e to the minus brackets xi minus xj squared. Okay. So with this competition function, when is the strength of competition maximized? And why might this be the case? So what's the maximum value that this can attain when it's written in this format? Yep. One. And when does that occur?
Xi equals xj.
Yeah. So strength of competition is maximized when xi equals xj, whereas aij is equal to 1. That's when it's maximized. So that's like the mathematical interpretation. What's then the biological interpretation of this? Why might we expect this competition function here to be maximized when xi equals xj? First of all, what does xi equals xj mean in terms of these individuals? Imagine this is two individuals who've come into contact with each other, individual with phenotype xi and individual with phenotype xj. Xi is equal to xj, they have the same phenotype, okay? So why might, if they have the same phenotype, why might you expect competition to be maximized? As opposed to different individuals who have a different phenotype.
Well, they have the same phenotype, perhaps they're always competing over the same resources.
Yeah, so suppose this represents something like the type of food that they prefer. This phenotype, maybe it's the type of seed that a bird likes to eat. If they prefer the same seeds, they're always going to be competing. If they prefer very different food sources, they're not going to be competing very often. Yeah.
So that interpretation is two organisms with the same phenotype, not just like the same. Because I'm getting confused. It's like same organism with the same phenotype.
Same phenotype, yeah, same phenotype. So, yeah. So if we imagine if we sketch out these phenotypes, again, it's going to have a similar form to before. If I put, let's call this Dij is difference between xi and xj. Then this Aij looks something like this. Not the best sketch, but it will do. Where it peaks at 1 when the difference between these phenotypes, this should be an Aij, the difference between these phenotypes is 0, okay? You can see here, as they get more dissimilar, then competition should tend towards 0. So why might this be the case? Competition is stronger between more similar individuals. I'll put it as more similar phenotypes here, just for clarity. Yeah, this might refer to like where they prefer to nest. Okay, so they're competing for the same territory. Okay, so that's the basic model set up. We've now, if we were to go back to this original equation here, Ri is just equal to R now. Aij, we have a function in terms of xi's and xj's in terms of our phenotypes, ki's in terms of phenotypes as well. So we can rewrite this equation in terms of our phenotypes, if we so wish. And we want to really know, like, what kinds of questions do we want to ask when we're trying to model evolution? One of the things we might want to ask is, okay, well, how do we expect this phenotype to evolve over time? Are we potentially going to end up at some optimal phenotype? Later in the course, we'll get on to questions about diversification, like, do we expect different phenotypes to emerge and for them to coexist? Do we expect those phenotypes to fluctuate over time? Do we expect the population to be driven extinct by evolution? These are all the kinds of questions that we can ask in these sorts of models. We can do that using adaptive dynamics, which is also known as evolutionary invasion analysis. And recall in adaptive dynamics, what we're doing is we're assuming that our population reaches some stable state. It doesn't always have to reach a stable state, but really for this course, we'll be focusing on it just when it reaches a stable state. And the mutations then have rare and small effects on phenotypes. The mutations are rare, and when they occur, they have a small effect on phenotypes. So can anyone remember from the last lecture, what effects do these assumptions about mutations have on our evolutionary dynamics, or how we model those evolutionary dynamics? I've just kind of said one of them already. So first of all, what does this assumption that mutations are rare have when we're trying to model evolutionary dynamics using adaptive dynamics? Any ideas, anyone? Okay, let's think of the converse. What happens if mutations are very, very common? Would you expect there to be many, many phenotypes in the population or very few? Who thinks there'll be many? Yeah, who thinks there'll be few? There'll be many. If there's lots and lots of mutations, you'd expect there to be lots and lots of variation, okay? So if mutations are rare, that means there's not going to be much variation, okay? So what this actually does is it means when we actually get to modeling this, rare mutations implies we're basically just competing residents versus a mutant. And resident population is at a steady state. So this is this process of mutation, invasion, replacement. We're not having to consider lots and lots of different phenotypes at the same time. We just consider one population, our resident, that has reached some steady state, and then try to assume that enough time has passed that it's reached a steady state before we introduce a rare mutation, and then see whether that mutation can invade and replace the resident that was there before. If so, then it becomes our new resident, and then we just repeat that process. But again, we would wait until that mutant reaches fixation and reaches a steady state before we introduce our next mutation. That simplifies the analysis greatly. Okay. What's the other thing? How about this small effects on phenotypes? What does that mean when it comes to our mutations? So if we imagine we have our resident phenotype XR and our mutant phenotype XM, what does that mean in terms of the relationship between XR and XM? Anyone? I don't want to keep asking Mark. It's not a trick question. If mutations have small effects on phenotypes, what do we expect XR to be relative to XM? Jamie, you look like you almost wanted to answer then.
It should be bigger.
Should be big. It's not necessarily bigger. They could be bigger, but like in terms of like magnitude.
The difference will be small.
Difference is going to be relatively small. Okay, so they're going to be approximately equal. Okay, if your mutations have relatively small effects on the phenotypes, when we introduce a mutant, remember these are just real numbers, right? As we've set this model up here, so XR is going to be approximately equal to XM. So our mutant is phenotypically similar to our resident. This becomes important a little bit later on. Okay. Because of this assumption here, this first one, that our resident is at a steady state. What this means is that we actually need to solve the ecological or population dynamics before we introduce our rare mutant. We need to know what's happening to this population when there's no variation in it. What kind of state is it ending up in? Is the population going extinct? Is it oscillating? Is it tending towards some stable equilibrium? Is there more than one equilibrium? We need to answer those kinds of questions. So always the starting point in these models is to first assume that our population is initially monomorphic. Remember, monomorphic, mono just meaning one. Mono being one, morphic being type. So you can think of this as one phenotype. You struggle to remember what monomorphic means. Contrasting with polymorphic, many phenotypes. We assume that phenotype is XR, with R referring to our resident. So like I said, we first need to determine the long-term ecological dynamics of this system, of this population, before we see whether this rare mutant can invade. So in the long term, we want to see what are the equilibria. So what happens when dnr dt is equal to 0? And there's only one phenotype in the population. Well, if you remember, if there's just one phenotype in the population, then we end up with our classic logistic growth model, R times by NR times by 1 minus NR over KR is going to equal 0. This then means that either NR has to equal 0 or NR has to equal KR. So when NR is equal to 0, the population is extinct. When NR is equal to KR, it's at its carrying capacity. Can everyone remember how to solve systems of ODEs, or at least one ODE to find equilibria? Steady states, right? So we set our differential equation equal to 0 and then solve that, make sure we account for all possible scenarios. Okay. The nice thing here is that because we're assuming this is monomorphic, and in this case, it's only one equation, it's relatively straightforward to solve. So we have two possible steady states, NR is 0 and NR is equal to KR. The next thing we need to do is we need to use linear stability analysis. Hands up who remembers linear stability analysis? A couple? Okay. Using linear stability analysis, we can see that the extinction equilibrium is always asymptotically stable. In other words, the population will tend there as t tends towards infinity. Well, how do we do this? Linear stability analysis, what we're doing is we're saying, okay, this is a nonlinear system, but we're going to approximate this nonlinear system close to any of our steady states that we want to, either NR is equal to 0 or NR is equal to KR. We're going to sort of disregard those nonlinear terms, and we're going to linearize around that equilibrium or steady state, and then see what happens to any small perturbation. Does that perturbation grow or does it decay? If that perturbation away from the steady state grows, then that means that we're moving away from it, so it's going to be unstable. If that perturbation decays, then we're going to move back towards that steady state. Okay, we do this by, in this case, looking at the derivative of this growth rate here. So this is the right-hand side of my original equation with just one phenotype. I take the derivative with respect to the population, here NR. So I'm doing dnr dt by dnr. It's taking this derivative and then evaluating it at each of the steady states. So the extinction equilibrium here is when NR is equal to 0. Like I said, I need those perturbations to decay away. Turns out that this needs to be less than 0. Okay. If you're not familiar with linear stability analysis, I've got all my videos for Math 360 online that do go through this. Linear stability analysis should have also been covered in the prereqs for this course. If you're not familiar with this, please let me know and I can send resources to familiarize yourself with that. The focus for most of this course is not going to be on how do we do linear stability analysis of these things, but it is a step that we need to take in order to get to the adaptive dynamics, okay? If you are struggling with this aspect, please let me know, okay? So for this extinction equilibrium to be asymptotically stable, in other words, for it to be an attracting state, this here, this derivative needs to be less than 0. So we take that derivative and we get r times by 1 minus 2nr over kr, evaluated when nr is equal to 0, has to be negative. So if we substitute in nr is equal to 0, this term here goes to 0. This implies that r has to be negative. So when r is negative, population goes extinct. I should say it makes some intuitive biological sense here. If the intrinsic growth rate of the population is negative, then the population is not going to be able to be sustained. It's going to die out. Okay. We'll often refer to this extinction equilibrium as being trivial. And especially in an evolutionary sense, it is often considered trivial because if the population is extinct, then no evolution can happen. So usually we only consider conditions when the population is able to persist. Otherwise, everything just kind of becomes trivial and this is uninteresting, okay? So the non-trivial equilibrium, in other words, the carrying capacity state, is asymptotically stable when, well, we do exactly the same process. So we take this derivative, so the growth rate of the population, dnr dt, we take the derivative with respect to the population, nr, and evaluate this when nr is equal to now kr. This is our carrying capacity. When is this negative? Well, again, we have r times by 1 minus 2nr over kr. When nr is equal to kr, when is that negative? We substitute in nr is equal to kr here, we're going to have 1 minus 2 in this bracket. So we end up with r has to be positive. We'd end up with minus r has to be less than 0, or in other words, r has to be greater than 0. So this is our linear stability analysis. The reason we've done this on our ecological dynamics before you even considered any evolution is because we want to make sure, first of all, that the population is viable so that some evolution can actually happen. And then we want to know when is it viable. We also want to know, in a more general sense, when we do these models, is this an asymptotically stable state? Is it something like a limit cycle, in which case we'd have to do more analysis? In this case, it's just asymptotically stable, the population will tend towards the carrying capacity. Like I said, the extinction equilibrium is trivial. No evolution can happen if the population is extinct. So we're always going to assume that the population is viable. In other words, the R is greater than 0, and so our non-trivial carrying capacity equilibrium is asymptotically stable. We're just going to assume that R is positive, and then we never end up in that extinction scenario in this model. Okay. The next stage, before I can move on, does anyone have any questions about the linear stability analysis? Or is everyone fine with everything that's covered on this slide? Okay, you're all fine. So we're now going to consider the invasion dynamics. Remember, this adaptive dynamics is sometimes called evolutionary invasion analysis. And this is what we did in the last lecture. We're going to consider the invasion dynamics of a rare mutant that has a very similar phenotype. XM is approximately equal to XR. So let's think about the dynamics of this rare mutant, DNM dt. This is only, I'll just go all the way back to the beginning. This is just this equation here, but for our mutant. Okay, this is where this equation is coming from. So DNM dt is going to equal the intrinsic growth rate R, which we know is positive, times by the number of individuals that have this phenotype, this mutant phenotype, NM. And then we're going to have 1 minus, in this case, I'll write it out in full, actually. We're going to have 1 minus AMR times by NR plus AMM times by NM all over KM, the carrying capacity for our mutant. So those are the exact dynamics. Again, this summation on the top is just the summation of the sum over Aij times by Nj. Yeah, for all the possible phenotypes here. And I'm doing this just in terms of the mutants. Remember, Aij is going to be the effect or the competitive effect of individuals with phenotype J, Xj on individuals with phenotype Xi. Okay. So this we can approximate. We usually just write it as being equals rather than as approximate. It's going to be RNM times by 1 minus AMR NR over KM. In fact, I'll call this NR star. Discuss why this is the case in just a second. This simplifies then down if we're our carrying capacity to 1 minus RNM times by 1 minus AMR KR over KM. Okay, so I've made a couple of simplifications there and haven't explained them yet. So the difference between this equation here and this equation here is I've dropped this term here, AMM times by NM. Any idea why I've done that? Maybe first of all, what is this term telling me? This AMM, what does that mean? Anyone? Strength of, so Aij is strength of competition between phenotypes I and J. So this is strength of competition between, sorry? What does the M stand for here? Mutant. Okay, so AMM is going to be competition between mutants. Okay, so this is two mutants coming into contact with each other, right? They're competing with each other. But I'm cancelling out this term. Why is that the case? Any ideas? I'm assuming essentially that this term is approximately equal to 0. Why might it be approximately equal to 0?
Because NM is approximately 0.
Yeah. So essentially here, we've got a quadratic term here in NM when you expand this out. So something that's linear in NM, like this first term here, NM times by NR, is fine, but this term here is going to be quadratic in NM. If NM is very, very small, then that's going to have very little effect relative to this first term here, the NR term. So we basically say interactions between mutants are negligible. So that's why we get rid of them. Okay, how about this difference here? So I've gone from NR to NR star, where NR star is our carrying capacity for our resident population. Why am I assuming essentially that there's no change in NR? It's a very similar reason to what we just discussed. These are my initial invasion dynamics. So this isn't true forever. This is just true for early stages when my mutant is relatively rare. Yep.
So NR star is the carrying capacity of our resident.
Yep.
So I guess since NM is so small, then NR must be like the same.
Yeah. So like, very early on, this only applies again as it's the invasion dynamics when our mutant is very, very rare. NR star is approximately, like, it's much, much larger, or rather NR is much, much larger than NM, and NR stars at NR star. So we can assume that basically as our mutant is trying to invade when it's relatively rare, it's not really going to be changing the resident population very much. I mean, most residents will be coming into contact with residents. There's not going to be much in the way of contact between, if you're an average resident, most of the time you're going to meet an average resident. You're not going to meet the mutant very often. okay, because it's rare. So basically, we can assume, and this is the great power of adaptive dynamics, is you're assuming that we don't have to now model our DNR dt as well at the same time. That would give us a system of two ODEs. We can basically say NR is approximately constant. So that's what we're really doing here. And then this final stage here on the right-hand side is just substituting in NR star is equal to KR. Okay, so I'm not going to fill in that text below, but that's just what I described. Mutants seem to be sufficiently rare that they don't affect each other. And all interactions that the mutant has are always with the resident. Okay. About 7 more minutes or so, and then we'll take a break. Okay, so we now have a system technically of two ODEs. I've just said that we're going to assume that one of them is constant, so we'll just come back to that in a second. We've got an equation for our resident, DNR dt, and we've got an equation for our mutant, DNM dt, okay? And what we really want to see is we're trying to see if that mutant phenotype can invade and then ultimately replace the resident. So in sort of a classical ODE sense, what we're really doing is we're saying, is the equilibrium, if this equilibrium here is NR star NM with NM equal to 0, is this equilibrium asymptotically stable? Again, this is essentially just linear stability analysis. We're seeing whether, if this equilibrium is asymptotically stable, that means that our mutant can't invade. We're going to get pulled back to this state where our mutant goes extinct. If the mutant can invade, then we're going to be pushed away from this state, which means that it's not going to be asymptotically stable. So we just need to consider the stability of this state, and it tells us whether our mutant can invade or not. So as before, we need to use linear stability analysis again. What we're doing is we're linearizing now around a system with two ODEs around this steady state here, AR0. We're dropping those nonlinear terms. Ultimately, the dynamics are given by a Jacobian matrix. Again, if you need a bit of a refresh on linear stability analysis in 2D, then let me know if you're not familiar with this. Our Jacobian matrix, if you recall, Jacobian, we take the partial derivatives with respect to our two variables. So our two variables here are going to be NR and NM, the population sizes for our resident and mutant populations. As by the derivatives with respect to those variables of our growth rates. So the NR dt, we'll have d by dnm, so the partial derivative with respect to our mutant of dnr dt. And on the second row, instead of dnr dt, we'll have dnm dt, the growth rate of our mutant population. And the eigenvalues of this Jacobian matrix will tell us whether our equilibrium up here, AR0, is asymptotically stable or not. If the eigenvalues of this Jacobian have both negative real parts, then that means that any perturbation away from that is going to decay away. In other words, our mutant can't invade. We'll just get sucked back to this KR0 state. Our mutant will go extinct. If one of these eigenvalues, at least one of these eigenvalues, has a positive real part, that means that our perturbation is going to grow. In this case, our perturbation is our mutant. So our mutant would then be able to invade. Okay, so we'd move away from the state. So we just need to now consider the eigenvalues of this matrix. Well, let's think, finding eigenvalues of a 2 by 2 is not super hard, but it's actually easier than it looks. So first of all, let's consider this term in the top left. So dnr dt, the partial derivative of that with respect to nr. Well, let's go back up here. We've already done this. And we've already assumed that r is positive. So we know that this value here is always negative. By definition, it has to be negative because we've assumed, or we've shown really, and then assumed that R is greater than 0, that this is asymptotically stable when we just have our resident population there, okay? So this term has to be negative. Okay, so that helps us a little bit. How about this term on the top right? We've got dnr dt, which is the rate of change of our resident population with respect to our mutant. Any ideas about what this might be?
0?
Yeah, great. Why do you think it might be 0?
Isn't the mutant constant?
So the mutant isn't constant, but it's very, very rare. So you're right that this is 0 because we're assuming if our mutant is very, very rare, then it's basically having no effect on the population size of our resident. So our resident here is now going to be unchanging with respect to our mutant because the mutant is so rare. So this is approximately equal to 0. I said equal 0 there, it should really be approximately equal to 0. I'll put it back to equals to 0 just because it try and avoid any confusion here. But we're essentially assuming this is now equal to 0. Okay, so we don't actually care about this bottom left term anymore, but you notice now that this is a matrix in lower triangular form. So a matrix that's in triangular form, can anyone remember how we find the eigenvalues? Yeah, it's just the entries on the diagonal, right? So this is nice and simple to solve because we know, remember, we're ultimately trying to see whether this is asymptotically stable. If this resonance equilibrium is asymptotically stable, the mutant can't invade. For it to be not asymptotically stable, at least one of these eigenvalues here has to be positive or have positive real part. This one here we know is negative. So everything just then depends on this term down here. So although we've had to, we've looked at this Jacobian matrix, in practice with adaptive dynamics, we don't even have to look at the whole Jacobian. We just have to look at this entry here. Is this positive? It's positive, implies invasion. Negative implies no invasion. Or in other words, the resident will win. We need to consider the sign of this term here to determine invasion. So in effect, we are doing linear stability analysis on this system of two ODEs where we've got our DNR dt and our DNM dt. But because of the assumptions we've made about the mutant being rare, we don't actually have to do the full linear stability analysis. We just need to look at this term. That's a lot easier. Okay, I think I'm going to stop there and give you guys a little bit of a break because that's been quite a lot of theory that we've gone through. Okay, so we'll reconvene in about 10 minutes. Okay, we'll start again, guys. Okay, so based on that little experiment of you guys closing your eyes and putting your hands up, it seems that a few people are like unsure about linear stability analysis. So would you guys like me to do a review lecture after the midterm on linear stability analysis? I see a few nods. Yeah? Okay. Just because it will be coming up as a sort of a necessity for when we're doing adaptive dynamics. Sometimes we will skip over that step and we'll just take it on faith that it is say like a stable equilibrium, but I will kind of expect you to be able to do that.
Oh,
Yeah.
So what material is the midterm up to?
The midterm is up to today, okay. But there won't be any linear stability analysis on the midterm. Okay, I will give you that tidbit there. So yeah, it could be anything from the first 6 weeks. Obviously, it's not going to be everything. So you might revise some things and they don't show up. Maybe those things might show up on the final. But I assume that anything that we've covered up until today will be. Okay, so I will pencil in a review session for one of the lectures on linear stability analysis to make sure that everyone's kind of on the same page. Yeah, good. Okay. Okay, so let's just recap where we were at. We were looking at the invasion dynamics of a rare mutant into this model of intraspecific competition. We just realized by looking at this Jacobian here that we only care about the sign of this term in the bottom right corner. If this term here is positive, then our mutant can invade. If it's negative, the mutant will die out. So this is all we have to worry about when we're figuring out our adaptive dynamics or invasion. Okay. Okay. So let's think about what this term is. So that term from the bottom right of the Jacobian, d by dnm of dnm dt. In other words, how is our mutant growth rate changing as with respect to the mutant growth rate? This is going to be r times by 1 minus, I'm going to write them explicitly as axi, axj, times by k of xr over k of xm. So all I've done here is I've just taken essentially this term here, the derivative of this with respect to nm. This is just linear in terms of nm. So the linear term drops out. This was the coefficient for that linear term, and I've just replaced these ki's with kxi's and aij's with axi, xj, just to remind you that these i's and j's refer to these phenotypes, xi's and xj's, yeah? And this thing here, I'm going to call w of xm, xr, so some function of xm and xr, and this is my invasion fitness. This is what I'm defining to be my invasion fitness of my rare mutant. Why is that the case? Well, we go back all the way back to the times we've, even population genetics models where we've been talking about fitness. If our fitness is telling us something about whether we can invade or not, or what is the fitness of one type relative to another. Okay, so this invasion fitness is going to tell us, well, the reason I'm calling this invasion fitness is because it's telling me something about whether this mutant phenotype is better than my resident phenotype. Yes.
So for the A term in this, are we going over all J or?
Oh, sorry, I put Xi's and XJ's there. My apologies. It's because I was talking about AI's and AJ's. This should be XM, XR. Thank you. So this is the effect of phenotype XR, my resident phenotype, on my mutant phenotype. Thanks for spotting that. If you recall, we don't have to sum over interactions. We don't have to account for interactions between mutants because mutants are rare. Okay, so let's find a condition on this competition term for the mutant to be able to invade. Well, the mutant can invade when this term is positive. So invasion if W of XM, XR is positive. So in other words, this term in the brackets has to be positive because we've already assumed that R is positive. So that means we need A of XM, XR times by K of XR over K of XM, so the carrying capacities to be greater than 1. In other words, to get a condition on this competition term, A of XM and XR has to be greater than K of XM over K of XR for invasion. This is telling us something about the ratio of their carrying capacities relative to the strength of competition. Okay, so the first stage, ultimately, when we kind of get more used to doing these adaptive dynamics modeling techniques, we'll be applying the same method to lots of different biological scenarios. In a similar way to when we looked at evolutionary game theory, we learned that, how do we find Nash equilibria? How do we find stable strategies, evolutionary stable strategies? How do we find mixed strategy Nash equilibria? All of those things. And then we applied them to lots of different biological scenarios, sex ratio, reproductive timing, competition, all of those kinds of things. We'll be doing the same here of kind of like learning a bit of a recipe. And like there are different stages to that recipe. And then we'll apply that same method to lots of different biological scenarios. Okay, there'll be things as well that we learn, additional sort of techniques that we learn along the way, but the basic process will be the same. So the basic adaptive dynamics process starts by determining up here the ecological dynamics. Okay, so we determine ecological dynamics when we just have one phenotype. Then we determine when can our mutant invade. Well, the invasion here is going to depend on its invasion fitness. And then the next thing we need to do is then say, okay, if we assume that that mutant is able to invade, so our mutant can invade whenever this equation here is satisfied, well, what happens in the long term? Once this process of a mutation arises, we see whether it can invade. If it can invade, it replaces the resident, and then we repeat. We keep repeating that process with our mutants replacing our residents if they're able to invade. If they can't invade, then we just stay with our current resident. To keep repeating that process, well, how do we know what happens in the long term? In the long term, we need to think about something called our selection gradient. Okay. So what is our selection gradient? Well, we define our selection gradient to be, here I'll call it S of XR, is the derivative of our invasion fitness, a partial derivative of our invasion fitness with respect to our mutant trait. And then we set our mutant trait equal to the resident trait. So that's the definition. Where does this come from? Well, if we just go back up here for a moment, this invasion fitness. Oh, sorry, yes.
On the slide, like, are we used to be that R is smaller than 0?
R is positive here. So in order for invasion, just to take a step back up here, for invasion, we need this term to be positive.
Right.
Because these are our two eigenvalues of the Jacobian, the ones that are on the main diagonal. And we want our mutant to invade. So we want this steady state where our resident is just by itself to be unstable. So for that to be unstable, we know that this eigenvalue here is already negative. This one has to be positive for it to be unstable, for this steady state to be unstable. In other words, for our mutant to invade.
Right. So then if that second term now that we said needs to be greater than 1, wouldn't that term there then be like, wouldn't the term you have highlighted if you have like the A, XM, XR stuff is greater than 1?
Thank you very much. I have got my inequalities around the one way. Thank you. Yeah. So this has to be less than 1, therefore, yeah, it has to be. Thank you. I can understand why you're confused by that. Got my inequalities around the wrong way. Yes, this clearly has to be less than 1 in order for this term in the brackets up here to be positive. And therefore, I mean, I should have got this from the biological intuition here. This is basically saying the ratio of your carrying capacities for your mutant to your resident must be less than the strength of competition imposed by your resident on your mutant. So that's always a good, if you can biologically interpret what this thing is saying, it should have clicked in my head then, if I've been thinking a little bit clearer, that the sign was around the wrong way. Okay. Thank you for identifying that. Okay, so this invasion fitness here is telling us, can this mutant invade or not? If we think about how successive mutants come into the population, if this term here is positive, if this term has a positive gradient, then that means that XMs that are greater than XRs are fitter. So they have positive invasion fitness. Yeah, so if this has a negative gradient, this term here, if this has a negative gradient, then it suggests that when XR is less than XM, our mutant is not going to be able to invade. In other words, we need to think about the gradient of this function. It tells us something about the direction of selection. So that's why we call this the selection gradient. Okay. So we take the derivative of our invasion fitness with respect to our mutant type, which is phenotype XM, and then we set XM is equal to XR. That might be a little bit unclear for why we do that. But it's important that we first take the partial derivative with respect to the mutant trait, and only after we've done that, then set the mutant trait equal to the resident trait. Okay. So why do we do this in this order? And why do we even do this second stage here at all? Well, our W of XM and XR is the invasion fitness of our mutant. And the reason XR features in that invasion fitness is because the mutant is not just invading into a vacuum, it's invading into an environment that is determined by the current resident population. Okay, so the recurrent resident population is determining the conditions under which our mutant is invading. So that's why it features in the invasion fitness. We take the derivative of our invasion fitness with respect to the mutant trait because we care about the mutant trait invading. So the mutant is the thing that we care about. You know, is the mutant having a slightly higher or slightly lower trait value than our resident population? Therefore, it's the gradient with respect to the mutant that matters. But then, why do we then set the mutant trait equal to the resident trait after we've done the operation? Well, we're assuming that they're phenotypically very, very similar, for one thing. So we're having very local mutations. And so what we really care about is, given a current resident population, so you're currently you have a particular value of XR, a mutant is about to arise. So given that it's about to arise, everyone currently has the same resident trait. So that's why we said our XM is equal to XR. A very slightly different mutant at that point, that point in this phenotypic space, is the invasion fitness going to be going up or down if we increase XM or if we decrease XM? Okay, so it's telling us here, when we're stood at that particular point just before a mutation happens, is the gradient positive with respect to our invasion fitness, or is it negative? That's a little bit of a weird one to get your head around, I appreciate maybe. The key thing to remember is, in terms of like operationally, we take the partial derivative with respect to the mutant trait because the thing we care about is the mutant trait. We then set the mutant trait equal to the resident trait because essentially we're assuming that there are very small mutations and these mutations are very rare. So that when we introduce a new mutation, just before we do that, we care about the direction of selection as the population is just before that mutation arises. Like I said, that is a little bit of a complicated thing. If you don't fully get the logic, at least understand the order. Okay. Okay, so we have a selection gradient now. When that selection gradient is positive, our trait is going to increase over time. If the selection gradient is negative, then the trait is going to decrease over time. In other words, if the selection gradient is positive, that means that XM greater than XR, means that W of XM XR is going to be positive, so it can invade. Otherwise, it's going to be negative. The question then is, what happens if this selection gradient vanishes? What happens if for some value, I'll call it X star, so for some phenotype X star, this selection gradient is equal to 0? Well, if we imagine that our phenotype is, just the real line, here, as I'm sort of moving in this direction, the selection gradient is positive, so I'm going to be moving in this way, say my X is going to be increasing. Over here, my selection gradient is negative, say, and I'm going to be moving in this direction. At some point, if I'm positive on this side and negative on this side, there must be a point where I'm equal to 0. Okay. At that point, selection is not pulling me in either direction. So this perhaps represents some kind of stable state. It might not always be stable, but it's some kind of interesting point. And we refer to this interesting point as a singular strategy. So this is the point at which our selection gradient vanishes when it's equal to 0. And it represents this potential endpoint of an evolutionary process because we're no longer being pushed at that moment to increase our trait or decrease our trait. So just as in the same way as when we find equilibria for a normal set of ODEs, something like that, we then find an equilibrium by in the case of, say, setting dn dt is equal to 0, we then think about the stability of that equilibrium. We do the same thing here, but in an evolutionary sense. When we say that a singular strategy is evolutionarily stable, or ES for short, when this value E, which is defined to be the second partial derivative of our invasion fitness with respect to our mutant trait, evaluated when our mutant and our resonant traits are both equal to this singular strategy, when this is negative. So what does this mean, and like where does this come from? Well, this essentially ensures that X star is uninvadable. You remember back to our evolutionary game theory, we talked about evolutionarily stable strategies as being uninvadable strategies. This is analogous to that. This phenotype X star, if this condition is satisfied, is uninvadable. Why is that the case? Well, if we think about this fitness gradient, sorry, not the fitness gradient, just this invasion fitness up here. This invasion fitness, well, it's a mathematical function. It's a function of xm, it's a function of xr, okay? We can take slices through this function and we can think about, okay, for given values of xm, xr, when do we have maxima or minima of this function? And maxima and minima are ultimately determined by second derivatives. Okay, so if you remember, if you've got a function, sorry, I've gone back a little bit too far here. Suppose you've got a function f of x is equal to x squared. You want to work out where there is an equilibrium, or where there's a turning point in this function, I should say, because it's not a dynamical system yet. Where is there a turning point in this function, and is it a turning point, a maximum or a minimum, right? So first of all, you work out f prime of x, in this case is equal to 2x. So you say turning point at x is equal to 0, right? That's analogous to finding your equilibrium in these dynamical systems. And then to work out, okay, at x is equal to 0, is this a maximum or a minimum? We look at our second derivative. In this case is equal to 2. Here we know from the shape of x squared, it looks like this. X is equal to 0 is a minimum. So this implies minimum. So in a fitness context, this would, if our value of E here is positive, then that means it's a fitness minimum. If conversely, if I change the signs now, if I make this minus x squared, then we would end up with a minus 2. We would have a function that looks like this with a fitness maximum. So when this is telling us about the curvature at this turning point, and it's exactly the same as what we're doing here. We've just got a mathematical function, we're taking its second derivative, and that's the curvature at that second derivative at this turning point, x star, tells us whether it's a fitness maximum or minimum. If it's negative, it's a fitness maximum. If it's a fitness maximum, that's kind of like being at the top of a mountain. You can't get any higher than that, at least not locally. So it's uninvadable because it's a fitness maximum. E being less than 0 implies x star is a fitness maximum. Just like with evolutionarily stable strategies in evolutionary game theory, it's uninvadable. So in the evolutionary game theory setting, we started off with our Nash equilibria where there was no better response. But evolutionarily stable strategies in evolutionary game theory had this additional condition that a strategy that had as good a payoff was just not able to invade. That's kind of the same here. This is just essentially ensuring that there's no better payoff, if you like. Not only there's no better payoff, but there's nothing that's equal to it. It's a fitness maximum. Does this make sense? I'm just going to nod to So when this condition is not satisfied, so if E is greater than or equal to 0, in this case here, E is greater than or equal to 0, then this singular strategy is evolutionarily unstable. In other words, it's a fitness minimum if this is positive. It's strictly positive. Intuitively, we might expect that something that is evolutionarily stable would be an endpoint of evolution. Okay, once you get there, you can't increase your fitness anymore. You're kind of stuck there. You're at the top of a mountain. You can't go any higher. If you have a case where something is evolutionarily unstable, that means you can increase your fitness. Potentially, you can increase your fitness by either increasing or decreasing your trait value because it's a fitness minimum at this point. So this tells me that this is probably not an endpoint to evolution, whereas this is. So as I've just gone through, just note the similarities with evolutionarily stable strategies. These things are related, but not quite the same. But in both cases, the strategy or phenotype that we end up at is uninvadable. A key difference here, though, is that in adaptive dynamics, an evolutionarily stable phenotype is locally uninvadable because we assume that mutations have small effects. Okay, so it's possible that there could be other phenotypes that are also evolutionarily stable. We did have this kind of situation in evolutionary game theory where you could have multiple evolutionarily stable states, right? So a sufficiently different phenotype could potentially still invade. It's just we don't allow for that. So for example, if I was to draw a cross section through my W of XM XR, I'm just going to fix XR in this case, so I can draw it in with just a curve. So I'm just taking a cross section through here. Maybe it looks something like this. Perhaps this value here is, I'll call X1 star, and this value over here, X2 star. Well, these are both fitness maxima. So in both of these cases, let's call it E1 is negative and E2 is negative. If I do my analysis, I would say, well, these are both evolutionarily stable strategies. They're attracting end states. If you know they're attracting from this, I'll retract that statement. We know that these are fitness maxima. We don't actually know if they're attracting. We know that these are fitness maxima, and so if you start there, you stay there. You can't increase your fitness by moving anywhere. Because we're assuming that mutations only have a local effect, even though this one on the right-hand side has a higher fitness, if you start here, you can only move a little bit left or right, which always decreases your fitness. Okay, so this is why this is evolutionarily stable. It's locally a local maximum, a local hilltop, if you like, even though there's a bigger mountain nearby. We just can't ever jump from one of these things to the other because we have this gradual process with mutants being very similar to our residents. Okay. See how we're doing for time. We're doing okay. Any questions on evolutionary stability? No? Okay. Okay, so we've detoured away from our model of intraspecific competition for a while. So let's go back and analyze it. So let's first think about what our invasion fitness looks like. So this is our W of XM, XR. You recall this was written as R times by 1 minus A of XM, XR times by K of XR over K of XM. So we had these functions written down at the beginning of the class. We're not going to go all the way back through the notes to get to them. A of XM XR was equal to e to the minus XM minus XR all squared. K of XR was equal to e to the minus XR squared. And then we're dividing by K of XM, which is then going to be equivalent to multiplying by e to the plus XM squared. So we're dividing by e to the minus XM squared, which is the same as multiplying by e to the xm squared. Okay, so these are just a collection of exponentials. They're multiplied together, so we can just add all the exponents together. So we'll get e to the minus, if we expand this xm minus xr all squared term, we're going to get a minus xm squared, a plus 2xm xr, a minus xr squared. We've then got from these final two terms a minus xr squared and a plus xm squared. So this plus xm squared and this minus xm squared are going to cancel. And then we've got these two here are going to come together to be minus 2xr squared. In other words, we can simplify this all down to be r times by 1 minus e to the 2xr times by brackets xm minus xr. This is just a case of substituting in the functions that we had defined right at the start for our competition and carrying capacity functions, and then combining exponentials and simplifying them, okay? So we want to find, first of all, our selection gradient. So we need to take our partial derivative. I'll do this in two stages. So if we work out our partial derivative of invasion fitness with respect to our mutant trait, well, our mutant trait only actually appears in one location here. So the first term is going to go to 0, and then we're going to have minus 2r xr e to the 2xr times by xm minus xr. Okay, so we have a minus r coming out the front. We have 2xr times by xm here, so that 2xr, when we take the partial derivative with respect to xm, this 2xr is going to come out the front as well, so we get minus 2r xr, and this minus r and this 2xr here, and then everything, the exponent stays the same. So that's the partial derivative of invasion fitness with respect to the mutant. That's not our selection gradient though. Our selection gradient, remember, we need to take the second step where we need to take that partial derivative and then evaluate it when our mutant trait is equal to our resident trait. You notice this works out quite nicely because when we set xm equal to xr, this is going to go to 0. So our exponent is just going to have e to the 0, so this is just going to be 1. And that with minus 2r xr. Now, our selection gradient now doesn't at all depend on our mutant trait because we've set our mutant trait equal to our resident trait. Okay, so we found our invasion fitness, we found our selection gradient. The next stage of this recipe is finding singular strategies. Do you remember our singular strategy x star, singular strategy x star, occurs at s of x star is equal to 0. So when is this selection gradient equal to 0? What values of x are? So in other words, x star must equal to 0. This is because we've already assumed right at the beginning that r was positive. So this is only ever a singular strategy when x star is equal to 0. The final stage then, at least as far as we're going today, is to determine evolutionary stability. So this is the stage that we just talked about. So we now need to take our second derivative. So we're thinking about the curvature of our fitness, of our invasion fitness. So we think about the second derivative of our invasion fitness W with respect to our mutant trait. To take our second derivative, well, just as before, we're going to have see, we don't have, we've only got our mutant trait here again. So we bring out a factor of 2xr again to the front. So we're going to have minus 4r xr squared e to 2xr, that's by xm minus xr. Just taking our second partial derivative organization fitness. It's just 2xr times by what we had before. Our evolutionary stability then is taking this second partial derivative and evaluating it when xm is equal to xr is equal to x star. In other words, our traits are all equal to this singular strategy. So as before, when we substitute xm is equal to xr, this is going to equal 0, just underlined in red. So the exponent's going to disappear. Then we end up with minus 4r times by x star, and x star is equal to 0. So this is equal to 0. So in this model, is my singular strategy x star evolutionarily stable?
Why is x star equal to 0?
Good question, Mark. You were right, by the way. Yes, x star is equal to 0 because this is our singular strategy that we've identified here. Which, to go back to your question you asked before, mathematical convenience is why I chose these functions, because things cancel down nicely and we don't have really horrible things. There's nothing particularly special about the functions that I've chosen in a biological sense, and why x may be positive or negative. It's really chosen for this for mathematical convenience. So x star is equal to 0 because this is the singular strategy, the only singular strategy that we've identified. Note also, we just had one singular strategy because this was linear in XR. Okay, you could have an arbitrary number of singular strategies, in which case you should, just as you would have in this function up here, there would be 2 singular strategies. So you would need to evaluate the evolutionary stability of each of them. Okay, just as if you have, for a dynamical system, you're trying to find equilibria, you might find more than one equilibrium, and then you look at the stability of each of those equilibria. Okay, so it's analogous. Okay, so this E is equal to 0. Jamie, you said that this means that it's not evolutionarily stable. Why is that the case? What's the condition we need for evolutionary stability?
Less than
Yeah, so E has to be less than 0, which we evolutionarily stable. This isn't satisfied, so no, E is not negative. This is basically telling me that in this setup that I've got with this particular competition function and carrying capacity function, that although there might be some potential endpoint to evolution, it is not evolutionarily stable. We're not going to go into today what that, like, the interpretation of that means. It just means that it's not going to be a state that we stay there forever. Okay. So let's consider a slightly different version of the model. Let's modify it a little bit, and we're going to assume now that our competition function is given by e to the minus xr minus xm to the power of 4. So not to the power of 2 anymore, to the power of 4. So since we're only changing the competition function, our ecological equilibrium, which remember was either our extinction equilibrium or our carrying capacity, they're going to be unchanged. And also their stability conditions remain unchanged because they just depended on R. We've not changed R at all here. Okay, so that analysis we don't have to redo. Great. We can skip straight to our invasion fitness then. Okay, so we need to find the singular strategy for the new model and determine if it's evolutionarily stable. And I have a show of hands. Who wants to do this as an exercise? Who would prefer me to go through it as a worked example. Okay. It looks like worked example wins. I'm shocked that you want me to go through it. No. Okay, before I get started, I'm just going to do a quick expansion here. So we've got this term here, which is a little bit more complicated than before. Before we had something that was quadratic. If we expand this, sorry, I've got these as XRs and XMs, but these should be XIs and XJs. In fact, I'll leave these down here as XRs and XMs because we're going to be talking about XRs and XMs. It doesn't actually matter which order we have this in. So write it as XM. We'll write it as XM minus XR. Okay. So if we expand this, we're going to have a minus XR to the 4 plus 4x 4xr cubed xm minus 6xr squared xm squared plus 4xm cubed xr minus xm to the 4. I think I've done that correctly. That's just expanding that just because we'll need it later on. So let's go through this recipe. So we have, first of all, invasion fitness. We can jump straight to the stage because above we said that none of the linear stability analysis for ecological dynamics has changed. We can just jump straight to invasion fitness. We already had this written in terms of our competition function A. So before that was written as R of 1 minus A of, I'm just going to abbreviate it here to A of MR, K of R, and K of M. So this is still the same. What I'm doing is I'm substituting in a different competition function, which we can write now as R times by 1 minus e to the minus xm minus xr power of 4 minus xr squared plus xm squared. This is our invasion fitness. Stage 2 is to find out our selection gradient. The selection gradient, if you recall, is the partial derivative of invasion fitness with respect to my mutant trait when my mutant trait is evaluated at the resident trait. I have a show of hands. Am I going too fast? Hands up if I'm going too fast. Okay. Again, if you feel that I'm going too fast at any stage, please just raise your hand, let me know. I'm more than happy to slow down. If I don't get feedback from you guys that I need to slow down, I'll assume that the pace is okay. It's totally fine though to ask me to slow down. So we've worked out our invasion fitness. That's stage 1. Stage 2 of this recipe is we're finding out our selection gradient. Selection gradient is our partial derivative of invasion fitness with respect to our mutant trait, when our mutant trait is then evaluated at the resident trait. So this one's a little bit more complicated now. Let's first of all just find out what our partial derivative is. So we're going to have a minus r times by the, let's see, plus xm's. Yeah, we're gonna, let's keep it simple by expanding and doing our derivative with this term here, and then we'll take this term separately. Okay, so we'll have minus, using this expansion I've got here above, we have a minus 4 xm cubed. That comes from the fact that we had a minus 4, sorry, we had a minus xr, sorry, xm to the 4. So we take the derivative of that, we're going to have a minus 4xm cubed. We're going to have this x gone over here. Let's do this x cubed term here, this xm cubed term. We're going to have 3 coming to the front. So we're going to have 3 times by 4, so that'll be 12 xm squared times by xr. This one's a little bit messy because it's obviously got a quartic in, so it's a little bit more expansive. What else do we have here? We are going to have our squared term here. The 2 we're doing for xm squared, when we take the derivative of this, the 2 is going to come to the front, so we'll have minus 12. So minus 6 times by 2, so we have minus 12 xm xr squared. This term here was linear in xm. So we just have 4xr cubed. And this here is basically all of these terms coming out the front. The minus xr squared term doesn't matter at all. And then on the end, we are also going to have derivative of xm squared. It's going to be 2xm. So that is what's going to come all the way out the front of my exponent. And then this is going to be multiplied by my exponent. So my e to the minus xm minus xr power of 4 minus xr squared plus xm squared. That was, and this is all going to be evaluated when xm is equal to xr. This is all kind of a nasty one to do just because of this quartic. All I've done here though is, this is just the chain rule. I've taken, to take the partial derivative with respect to xm, I take the partial derivative of this, the exponent with respect to xm, that gets multiplied out the front. So that's where all of this comes. This comes from here. Then I have e to my exponent, which doesn't change. This minus r comes from the fact that I had a minus r out the front, and this constant term goes to 0. Okay? If you're not sure about the actual algebra here, I hope I haven't made a mistake, but this is essentially just using the chain rule. Okay? So we can simplify this. We're going to end up with minus, if we substitute in xm is equal to xr, note again, when xm is equal to xr, this term to the power of 4 is going to go to 0. We're going to have a minus xr and a plus xr, both of those things squared. So this whole exponent is going to go to e to the 0. In other words, it's going to be 1. So that's nice. So we'll have minus r at the front times by, again, we're going to substitute in xm is equal to xr. So I'll write it all out. So we're going to have a minus 4xr cubed plus 12xr cubed minus 12xr cubed plus 4xr cubed plus 2xr. What I've done here is I've substituted into this here, xm is equal to xr. And you'll notice here that these cubic terms cancel. And we just end up with minus 2r xr. Seem to have lost a page, so I'm going to duplicate a page. Okay, so we found our invasion fitness, we found our selection gradient. The next stage, can anyone remember what the next stage is? Invasion fitness, selection gradient. Can anyone remember what we do next? Yep.
We're gonna look for our singular strategy.
Perfect. So third stage to this recipe is find singular strategies. That's when some value x star, where s of x star is equal to 0. In this case here, that implies that minus 2r x star must equal to 0, or again, x star is equal to 0, since r is positive. So it turns out, in this particular case, our singular strategy is the same as what we had before. What's the fourth stage? Fourth and final stage as far as we're concerned today.
Check for evolution.
Evolutionary stability. Again, this is going to be a little bit messy. We're now going to have to find our second partial derivative of our invasion fitness with respect to xm. Here I'm going to separate it out before doing the substitution. This is rather nasty. In fact, I'm not going to write this all out because it's a little bit of a waste of time. Take it on trust for this one in particular. I'll leave it as, I'll do a classic mathematician thing. I'll leave this as an exercise to work out what this is. Mathematician's excuse. Okay. I mean, at the end of the day, all that is taking a second partial derivative. You're applying the chain rule. It's a bit laborious. If you do that, you end up with your E, which is going to tell you your evolutionary stability, evaluated when your mutant and your resonant trait are both equal to the singular strategy of 0. It's going to be minus r times by 4x star squared plus 2, and x star is equal to 0. So we end up with minus 2r, which is negative. You see that in this case now, x star is evolutionarily stable. But evolutionary stable now. So all that we've done differently in this version, if you recall, is that we've changed the nature of that competition function. So it's telling us something that, okay, if the nature of competition changes, we haven't kind of discussed what that nature means, like what it means that we've done is we've changed that function. We've gone from something that wasn't evolutionarily stable to something that is evolutionarily stable. So this tells me if we end up at x star is equal to 0, whatever that phenotype corresponds to, once we get there, we stay there. Okay. Very last thing, which is related to this. If we imagine the graphs then of these two scenarios, I'm just going to draw them as functions of f of x. We've got something with e to the minus something squared and e to the minus something x, e to the minus something to the power of 4. Okay, e to the minus something squared and e to the minus something to the power of 4. So let's think about these as just functions f of x. If we look at it, e to the minus x squared, we can think of this as f of x. So this was our carrying capacity function, looked like this. It was also what our competition function looked like as well. If we just, if x we define to then be our difference between our phenotypes, looks like this. And then what we had in the second scenario here, if we look at e to the minus x to the 4 as our function, when we set our competition function be like this, this is basically saying competition is strong between phenotypes that are very, very similar, but then a tiny bit of divergence away from this means that competition goes towards 0 very quickly. So if you think of these as our two competition functions of these two scenarios, This is basically saying when the competition function is wider, so phenotypes that are moderately similar still have an effect on each other, then we don't end up with evolutionary stability. Whereas when competition between phenotypes that are moderately similar is very small, imagine taking a slice, say through here, and seeing the strength of competition on the red curve is much lower than the green curve, or whatever these values happen to be. It's saying something about the nature of competition leading to stability. And it's saying, well, the narrower this competition function is, the easier it is to get stability. We'll talk more about how these functions, the nature of competition functions, the nature of carrying capacity functions relative to phenotypes affects things like stability. It can produce things like diversification as well, a little bit later on in the course. So what might we infer from this sketch? Well, written down here, it suggests perhaps in this relatively simple model that there is a unique singular strategy which is only evolutionarily stable when the competition function is narrower than this carrying capacity function. It's a speculation, but it's telling us something about two fundamental biological properties of this system and what the relationship must be between them in order for us to get some kind of evolutionary optimal outcome. Okay, that's been a lot today. I appreciate we have kind of gone through a lot of new material. We will be repeating this process of adaptive dynamics in the coming weeks, so don't worry, we will be going over this again and again and again, okay? Have a great weekend, and I'll see you next week.